Hello, my name is Mareike Kampmeier and I'm working for the Helmholtz Center for Ocean Research in Kiel in Germany. And my presentation is about the automation and autonomization of munitions detection in Baltic Sea dump sites. First of all, I would like to introduce the BASTA project. In BASTA, we are boosting applied munition detection through smart data integration and the application of artificial intelligence workflows. It's coordinated by the GEOMAR, and partners are in Belgium, the FLIS Institute, and the company GTEC, and also the German company EGIOS. Additionally to that, we have partners inside the industry like TenneT, DEME, and Vattenfall, among others. Our research areas are mainly inside the Baltic Sea, inside the munition dump sites Kolberger Heide and Lübeck Bay. The motivation for us was actually that the offshore explosive ordnance disposal is usually structured in 4 phases, whereby the first phase is a preliminary survey, so that means this is all the historic work prior to the survey. Then it comes to phase 2, the technical survey, where the area is mapped and the data has to be processed and analyzed to find possible target points. Then it comes to phase 3, which is the further investigation of possible target points, so to say the validation or ground truth of phase 2. And then if this has been conducted and a list of target objects is generated, then it comes to phase 4, the clearance and the disposal. We will focus on the phase 2 and phase 3 because those are the main time-consuming phases. There are a lot of technique and vessel time is needed, and it has quite a lot of potential also to improve the processes here. So we think it's needed to instantly evaluate the generated data on its quality, because you have to be instantly sure that your data is actually fit for the purpose, for the kind of UXO which you are looking for. The second step is that we instantly also want to generate a target list, so to make this process much more faster and reliable. And the third is, to make it even more time efficient, is that we apply autonomous processes or methods so that you can map the area of interest and instantly or simultaneously start mapping with detailed surveys of target points. This is also how we started. So we did high-resolution multibeam-mapping, which is one method for surveying. And as you can see here, these are 3 multibeam raster with the bathymetry, and it becomes clear very easily that the resolution of the multibeam is actually essential. So first of all, we start with 50 centimeter resolution, and of course you can see some objects there, but it's hard to identify those objects. If it's a cluster like this, might be more easy, but if you only have single objects, it's quite difficult. So we would always suggest to or recommend to have at least 25 centimeter resolution per pixel, because then you can see single objects, but you also already get an idea about the shape of the objects. And this even improves with 15 centimeter resolution, but this is quite ambitious for large area surveys. Nevertheless, also additional to the multibeam data, you also get backscatter data for the multibeam. And here's an example for 25 centimeter resolution, where you can see some objects, and if you increase the resolution to 2 centimeters, the objects are really nicely displayed, so the shape is very good to see. The only problem is that they do not have one characteristic amplitude signal, because the amplitude is depending on the orientation of the UXO inside the multibeam swath. So the next step is to evaluate the data quality. So therefore there was a data quality factor matrix developed inside BASTA, and you can put in standardized, or you can choose standardized objects, put in their dimensions. These are the objects which you target to find inside your data, and then you can check your data whether it's capable to display those objects. For example, here with Multibeam, there are two examples. One is the data point spacing, one is the footprint, and whereby the data point spacing in this raster data set seems to be very good, as the footprint won't be enough in most areas. So this you always have to keep in mind when you generate training data for the artificial intelligence algorithm. So you do want to have the most reliable data that you can get. And this is the first evaluation what you can do. For generating the training data set, you start first of all with manual target picking by human experts. This is the first step. And here is an example. So we took the multi-beam, the bathymetry hillshade in the background, and we asked 6 experts to do target picking in one specific area. And this is the outcome of that. So the colors indicate how many experts chose this object and classified it as a UXO. And blue means only one expert decided that this is a UXO, and the red indicated all 6 experts agreed that this is UXO. And what you can see here is the experts usually they rely on they take the shape and the size of the object. So for example, this ground mine, a cylindric object it cannot be a rock, so the shape is the most distinct characteristic, which is most important for the detection. Secondly, also patterns can be a hint for UXO detection. For example, here we have objects in a certain size with a very defined distance in between, so this could be some kind of en route dumping, for example. Nevertheless, there is so much disagreement, so we really need ground truth data. And what we use therefore is our AUV, which is equipped with a camera and a magnetometer. And this is an example of an AUV survey. So these are the survey lines around this munition site. And this is one piece of a photo mosaic. This area is over here. And you can easily detect all the munition objects which are inside the photo mosaic. And you can also compare it to your, for example, multibeam data and see what was still detectable inside the multibeam data and what kind of size you wouldn't see anymore. Additionally to that, we also use magnetics. So we have a gradiometer installed at onto the AUV, and this is an example for a gradient plot for the small target area here. So this is also used for ground truth, which will validate the manual picked targets to improve the training data set for the artificial intelligence algorithm. So once we have our training data set, we can use it for training the convolutional neural network, which is our artificial intelligence algorithm. So it works that we have, first of all, of course, we have our survey data. We checked the quality of our survey data and used this for generating the training data set. We did the annotations, we validated the annotations with the ground truth, and all this data then goes into the network. So the network is actually structured like a brain, and it has different layers of neurons which are all connected to each other. In this example, this is just a very basic network. What we use is a so-called convolutional neural network, which has many more layers than only one. So there's a stack of dozens of neural layers, and each layer acts is like a filter, and the data can be so it goes from one layer to the other, and in the end we get an output where we have this is UXO or this is no UXO. And this output again can be tested against testing data, which is already annotated, or we can also ground truth it again. And then this is an iterative process, and with each run the model will improve itself. And in the end we will get a target list which is objective and reliable. To sum up this work is, first of all, it's essential to have good quality and good quality data, and in this case this means high resolution multibeam mapping. You want to have the best resolution which you can get to get as many information, like the shape, for example, from the targets. Secondly, we have to do a data quality evaluation so that we can get instantly rid of the data which is not good enough to detect the objects which we would like to see, or maybe we can decide, okay, we have to map there again. And we can use this data then for generating the training database. And this is still based on human expert annotations, because the ground truth of large areas takes a lot of time. But the better the quality of the data, the more reliable the results will be. And then we can use this data to train the convolutional neural network. There are some disadvantages of this network, and the biggest disadvantage is that it's highly dependent on the input data. So if you put rubbish in, you will get rubbish out. So it's really dependent on what was annotated, and the less data you have, the worse the model is going to be. So to train the model very well, you need a huge amount of training data. And also another advantage is that such a model is like a little bit like a black box. So inside the deep layers, it's not possible to see what it's doing in there. So you get an output. You can fine-tune the model and do some weighting and some filtering until the output fits, but you do not know what happens inside here. And generating training data, this is a very complex task, and also training the model is quite complex. But once a model is trained, it is very convenient because it can recognize even complex patterns. So as I said, the human experts usually relied only onto the shape and the size of the UXO, and the complex model might be able to detect even more specific patterns which a human wouldn't be able to see. And the more data we have, the better the models are. So if we get new data, we can also always keep on training the model with fresh data, and it will always improve. So it's possible to scale it with respect to the object and the data complexity just via adjustment of the network. And also it will be possible to transfer to other data inputs. So in the end we will also be able to use it for sub-bond profiling data or photogrammetry, magnetics or side scan data. And as soon as it's running, it's definitely suitable for automation processes. And this is exactly what we are focusing on. So first of all, of course, we want to improve the model, also by including additional sensor data. And then we want to transfer this model also to other areas. So now we used it in specific water depths, for example, and different or specific background geology, and this should be transferred to other areas as well. And the main vision is to implement this intelligence to an AUV. So the dream is that the AUV just goes into the area, maps the area, calculates by itself, and gets some target points, and decides by itself where to go next to do some detailed mapping, maybe mapping with additional sensors, and to do the interpretation of the data and the target list by itself. And with this, I would like to close my presentation. Thank you very much for your attention.